All right, so theme 4 was actually just carrying on from this in a way, because if you remember, theme 4 was dealing with the normal distribution. So it basically looks at the normal distribution in a little bit more detail, okay? Because it was a little bit different to what we were looking at with the binomial and the Poisson, the discrete distributions. So we looked in a little bit more detail. We understood some of the properties of the normal distribution. Ultimately, we said, hey, look, do you know what? The normal distribution follows this curve. Effectively, we're saying that in the middle here, we have the mean, okay? The most likely outcome should be in the middle. And then from this, we basically said, okay, if we measure 3 standard deviations each side of the mean, we should expect 99.9% of our data pretty much, okay? So yeah, so pretty much 3 standard deviations each side of the mean. So this is mu plus 1 standard deviation, mu plus 2 standard deviations, and mu plus 3 standard deviations, and the same in the other direction. So mu minus 1 standard deviation, mu minus 2 standard deviations, and mu minus 3 standard deviations, okay? And then from this, we basically said, okay, I can understand different properties of the normal distribution, particularly useful if you're dealing with things like outliers, right? We said that the outlier justification said, if any values lie beyond 3 standard deviations of the mean, it's going to be an outlier, in this course at least. That's the way which we define it, okay? Because it's such a low probability of occurring, yeah? So yeah, we looked at different properties to do with that as well, okay? There was also a second part to this, which fed into the central limit theorem, okay? So CLT for short, central limit theorem, okay? And I literally said, well, okay, if I'm just dealing with one sample, I might have X is normally distributed with a mean of mu, let's say, and a standard deviation of sigma, so the variance will be sigma squared. By the way, actually, before we jump into the central limit theorem, you remember that there was the standard normal distribution that we used, right? So we said, well, actually, a lot of the time we're working with the standard normal distribution, which just has a mean of 0 and a variance of 1. Yeah, and the reason why we use this distribution, can anybody remember why we use this distribution as opposed to this one?
It's easy to calculate the... So we haven't... It's easy to calculate the probabilities commonly because standard deviation is just... It's always the same parameters.
Yeah, perfect. So we literally said, well, look, if I ask you now, what's the probability that X is less than 4 given this particular distribution? You're like, well, how am I going to work that out? Well, then that's when we jump over to our tables. So the tables literally say, well, look, if you have a distribution with a mean of 0 and a standard deviation of 1, or variance of 1, it's the same thing, well, I can tell you what the probabilities are going to be at specific to 2 decimal places, okay? But in order to get from here to here, we need to standardize. Good. Can you remember what the formula for standardization is?
Z eşittir equals to
X.
Minus this
Mu.
Yeah,
divided by
sigma.
Good, well done. The standard deviation. Excellent. So that's how you convert it, right? If you have X, you want to find the probability that X is less than 3, for example. You take away the mean from it, divide by the standard deviation, you've got that distribution. Okay, that's the value you should look up in that distribution anyway. Okay, so being able to standardize and things like that. Just be aware that exactly the same thing that I showed you in the first part, where we dealt with the Poisson distribution, if you choose with the normal distribution to use your calculators online, that is totally fine. I'm totally fine for you to do that, but you must show this process of standardizing in the process in so doing. Okay. Cool. Okay, and again, this kind of thing will come up in hypothesis testing. Okay, so when we look at hypothesis testing, if we're using a Z distribution or even a T distribution, it's still the same kind of idea. Yeah, we're going to have to kind of understand the normal distribution, the shape of it, the properties, etc. When that kind of comes up. Okay, so once again, these themes are kind of interrelated in many ways. So okay, let's think about the central limit theorem then, which is related to the normal distribution. We literally say with the central limit theorem, if I have a distribution, X, which is normally distributed with some mean and some variance, okay? This here, if you like, is just for one sample. So basically, I might go out and I might collect a data set. For example, I go around everybody at the college at the moment, okay, and I ask them, what is your mean age? And then I can be able to find the standard deviation / variance from that, Okay, so that's one sample. I've gone around today and asked everybody in the college. Okay, but clearly, as we've discussed with theme 1, so again, theme 1 is coming up, it's better to collect a bigger sample because then you get a better approximation of what's happening. Clearly, if I ask just you three, I'm not going to get a good distribution of what the ages are in the college, for example. Okay, so let's suppose that I go around and I do this on multiple days, so I collect multiple samples. So how would this distribution change for, let's say, n samples? For multiple different samples, how would this distribution change? So I should be able to find the mean of this distribution with n samples. It will still be normal, but how will each of these parameters change? What will happen to the mean? If I go around today, ask everybody in the college what their mean age is, right? So what their age is, then I can find the mean from that. And then I do that on maybe every single day. So 7 days a week, 7 samples, right? How would the mean expect to change?
Population mean?
Good, exactly. So you're expecting that it shouldn't, basically, right? So this parameter here shouldn't change. You don't expect the mean to change depending on how many samples you collect. Okay, it should be relatively the same. What about the spread of the distribution?
Divided by n.
Good. The spread of the distribution, sigma squared, should reduce by a factor of n, right? The idea is that obviously if you go out today, you collect everybody in the, you collect data from everybody today in the college, you expect that distribution to be quite sparse. Okay, there might be some people that are say 30, some people that are say 20, and some people that may be even sort of older than that, whatever. So it's quite a wide distribution. But what you should expect to happen is that as you collect more and more samples, so you do this more and more often, okay, you collect a bigger sample size, you should expect that the distribution should become less spread out. In other words, they should become more centered around what the true population mean is, okay? So I don't know what the true population mean is, ages in the college, maybe about 20 odd, but that's where you expect the distribution to be centered, okay? So the distribution should reduce in spread. Does that make sense?
Yeah.
Yeah? Now, clearly, I'm just looking for one parameter here. I'm just looking for whatever the random variable is and then taking the mean of that random variable. If I wanted to look for a difference in the means, which is particularly useful for hypothesis testing. So if I want to look for x1 take away x2, well, okay, it's still going to be normally distributed. And I'm just going to look at the means. So the means are going to be subtracted from each other. And likewise, I can just think about what the variances would be as well, okay? So that would probably be sigma 1 squared take away sigma 2 squared. Is that okay? Right? Now, if I look at the mean of each of those things, so if I look at it for, if I look at it for multiple different samples, okay, which is ultimately what I'm doing, still got the difference in the means, but the thing which is going to change is this second parameter. Can anybody remember how it's going to change? So if I want to go out and I want to collect a difference in the means, it's going to be normally distributed. I'll have a difference in the true mean values, mu1 take away mu2. What goes over here? In fact, just before we go there, so you can carry on thinking about that, just before we go there was a slight mistake that I made there. If I go back to the original distribution, x1 take away x2, it's going to be normally distributed. I agree with this bit. I said it was going to be sigma 1 squared take away sigma 2 squared. Is that right? I mean, it's not, because I brought it up again. What's wrong about this?
Sigma 2 squared divided by n.
Okay, so we're going to go there quickly. Perfect. So we're going to divide both those things by n when we look at multiple samples. But just looking at this for the moment, just looking at it for the one sample case, or one sample from each case, what's wrong about this? It's not sigma 1 squared take away sigma 2 squared. What's different? plus, right? Think about it. These are two different random variables. So if I combine together, going back to the last theme, if I can combine together the variance of x1, take away x2, that's what I want to find. I want to find the variance of this distribution. Yeah? Well, okay, this is exactly the same as the variance of x1 plus the variance of negative x2. Does that make sense? Just thinking about your rule which we had, the expectation algebra. Variance of x1 plus negative x2 is the same as variance of x1 plus variance of negative x2. And again, if I pull that negative out, are you happy that becomes negative 1 squared? That's just a constant. Does that make sense? Yeah? So hence the reason why it's variance of x1 plus variance of x2. And of course, you know, I did that just because I was testing you, right? I didn't make that mistake to start off with. No, I'm only joking. So yeah, in this case, because I'm looking for a difference, it's still going to be a positive, right? It's still going to be a plus, okay, for this very reason. But okay, my question still stands. If I want to combine lots of these samples together, so I want to take the mean of x1, the mean of x2, and I want to look for a difference in these two mean values. Let me write that a little bit neater. Well, it's still going to be normally distributed on the same principle that when I was looking for a mean of just one particular variable, then it's still going to remain as mu. So in this case, it's going to remain as mu1 take away mu2. However, variance will change how?
Sigma square 1 divided by n plus sigma 2 divided by n.
Good. So it's going to be divided by the sample size of each of the things.
Yeah.
Perfect. Well done. Okay, so that's how that changes, right? Now, like I say, it still follows the central limit theorem idea, okay? And it still follows kind of similar idea as what we were doing over here. However, this is more to do with hypothesis testing, okay? So when we're looking at hypothesis testing and confidence intervals, which is the next theme, that's where we're going to be using that, okay? Because obviously when we're looking at hypothesis testing, usually we're going, can we find a difference in the mean values? Or can we find a difference in the means? Or can we find hypothesis testing that the mean value is equal to a particular value based on this particular number of samples? Does that make sense? Okay, so having an understanding of the central limit theorem is useful. Ultimately, it just boils down to these formulas, and these formulas are in the formula sheet. So you don't have to worry about memorizing them or anything like that, okay? But are there any questions with anything we've done there for the normal distribution?
Okay.
Okay?